We started in on compressor wheel design work when I realized that I couldn't modify Evo 9 turbochargers because they turned the opposite direction. In the cases where they'll go ahead and listen to you and take your advice, they'll call you up and go, oh my God, I just took 76, 75 off and put your 72 millimeter on there and we gained 6 miles an hour. Well, how did that happen? I'm not big on people trying to buy and sell used turbochargers, but you'll see people say, I've got this turbocharger, just pull it off, it's got 0 shaft width. And I was like, well, that's bad. So you get the guys sometimes that are like, the turbo lasted 1 pass. And I'm like, well, tell me what happened. Well, it was making 920 horsepower, man. I put the slicks on it and man, it cut a 160 foot. And okay, that kind of explains why it's all melted together. You see Chinese companies taking Garrett's complete catalog of turbochargers and making copies of the whole damn thing. And Garrett and their entire legal department is powerless to stop them.
Maybe he's got a 62, 62 or 64, 66. And he wants to switch over to Xona.
Standard comparing to Turbine X PTE in the sub 72 millimeter range, we just whip them. I do a 540 Mick whipping on them.
Welcome back to another episode of the Street Alpha Podcast. I'm your host, Tukes, and we are back in Texas for another banger with you guys. So we are at Xona, or what is this?
Force Performance.
In partnership with
Xona.
Mm-hmm. And you guys have had years of experience with turbos specifically, and you guys have really been pioneers for like innovating kind of a new technology for turbochargers for the most part.
That's true, and thank you for pointing that out. We have, me and my partner Greg Jones from Tile, we have spent a lot of energy and resources developing compressor technology and turbine arrows that have, I think, my opinion, been really pivotal in the performance of the market over the last 2 decades, for
100%. Yeah. So before we even start, just so you guys know, this is Robert. Let's give a round of applause for Robert. So yeah, appreciate you. Thank you so much.
My pleasure.
We just knocked out some street tacos, which was really good.
Yeah. You said you had need. I was like, well, hang on a second. Let's just get some tacos in here.
Starving. But that was
come to Texas and not get some street tacos.
No, I've never had street tacos, but those are really good. So thank you.
Arroyo's, Van Alstyne, Texas.
So yeah, we're going to talk about. Well, I'm pretty interested in knowing pretty much what sparked the interest into turbo technology and what you guys are doing and what you guys have been doing over the past, how many
I would say
now?
Necessity was really the main driver. We started in on compressor wheel design work when I realized that I couldn't modify Evo 9 turbochargers because they turned the opposite direction.
Damn, it seems like everybody started with Evos.
That
a lot of the top guys.
It was the DSM, and then it was the Evo and the STI and GTRs, and now 10 cylinders. And that's kind of the path. And a lot of people split off, instead of 10 cylinders, went to BMWs. But it's kind of the family tree there. But a lot of people, if they were around in the 90s, they were DSM people, and if they were around in the 2000s, they were Evo guys. Right. But it was the necessity of they're not existing parts that I could adapt. Okay, so when the Evo 8 came here and people wanted to push the power on them, this is in the era before tubular headers were just on eBay. So it wasn't like you could just have a $300 header solution if you wanted a basic header solution. So having something that fit in place of the factory turbo was a really big key feature. And I guess it still is in a lot of ways. But the problem with the Evo 8 was that instead of the wheels spinning in a clockwise direction, it spin in the anti-clockwise direction. Okay. So that meant like when I go to the wall of wheels, there's not wheels that turn that direction, because it was very uncommon for prior to 2000, us seeing these in 2008. I mean, in the Evo 8, in the 2003 year model, we hadn't really seen a lot of reverse rotation turbochargers. I definitely hadn't, because it wasn't present in any regular turbo that I'd run into yet. Yeah. Okay. So, and it became a lot more popular. But since there wasn't like, oh, well, let's just rob this wheel out of this Garrett turbo, or let's rob this wheel out of this other Mitsubishi turbocharger, and we'll retrofit and adapt and modify like all the hybrids that I'd done prior to that, the 2003 time period. We just had to make a wheel, right? Because it's like it's not like a Star Trek. You just put it in there and you go, make me one of these, Earl Grey tea hot, that doesn't work that way.
Yeah.
So, but Greg over at Tile was really big into advanced machining processes. So he had a couple 5-axis machines and the level of precision necessary to do this. And so right around there, 2003, 2004, we started to whittle our first wheels out of billet aluminum. And why do we make it out of billet? Well, I couldn't afford the tooling to take a wheel design and then buy the tooling and make 2,000 compressor wheels just for that one application. So since we already had the machines on hand, it was easier to just make them one at a time, because the volume of them that we needed was relatively low.
Right.
So we started that way, not because we wanted aerodynamic benefits necessarily, but just because we needed a part. So that's how that started, now out of necessity. Now, what happened after we made the first ones is that we realized, well, now that we can do it, that kind of worked as a proof of concept. What else do we want to apply this to?
Yeah.
And so that's when we started to get into the aerodynamic design side of it, rather than just is it possible to machine them?
Right.
Okay. So right in there, we started working on actually designing wheels just from scratch. Okay. And that's kind of a long process, and it does take people that are well trained in that industry to do it. But we hired those people, and we came up with really nice compressor wheel, the HTA compressors that we put in a lot of 35Rs. Really popular to have a 3582 HTA or a 3586 HTA turbocharger in that time period. And there were years you go to the DSM shootout, and the whole 9-second Evo class is just full of 3586 HTA cars. It's just a dozen 9-second Evos running in that class.
Yeah,
and that was really a cool period of it, and that's how it started, and that's where it went. We went from necessity to, okay, now that we know how to do this, let's focus on splitting hairs and doing it a little bit better, and just continuing to make it better and better and better.
Right.
And we're several generations of wheel down the line from that now. And revisions kind of get implemented annually also to reduce the internal stress of the compressor wheels, improve the materials of the compressor wheels, reduce the inertia of the compressor wheels, reduce the blade thicknesses of the compressor wheels, and just get more flow out of the same size wheel.
So what was it, aside from the fact that there wasn't much on the market, that made you want to really focus in on trying to be different with turbochargers?
Well, ultimately we built a lot of those 3582s and 3586s based on Garrett product. And it started to become apparent that we didn't really want to rely on Garrett to provide cartridges for it. Okay. And so getting unaddicted to Garrett was an important stage of it.
Okay.
So we ditched the Garrett distributorship, and we started Xona Rotor, and we started to make all the rest of the parts also. I had already been making the turbine wheels for years because I was making custom turbine wheels for my hybrid turbos, the Subaru DSM and Evo.
Okay.
So we had all the pieces there, except we needed to make friends with a German bearing manufacturer and start.
It's time to kind of get.
So it was just really the time to take the next step, and did we underestimate how difficult and what the challenges were going to be? For sure. Yeah. We just had, starry eyes and, going to set the world on fire. We're going to be the next big turbocharger company ever to exist, and it's been a decade since then now since we launched Xona Rotor. So we've come a long way, but, is the climb always a little harder than it looked when you were at the bottom? Yeah. But, we're really happy with where we've got now, and the performance we have with the newer generation of our XRE compressor wheels, our HTE model compressor wheels. We just continue to develop that, and most of that happens in the engineering department over at Tile. Right now, that's where a lot of almost all the design work is handled there. And almost all the manufacturing work is handled at the tile location in Owasso, Michigan also. And we are primarily involved on the Xona Rotor side in building and assembling the turbochargers, dealing with the service aspect of the turbochargers.
Right.
Initially, we built most all of them, but then we built in a turbo shop at the Michigan location, and a lot of units get built there and balanced there now too. We were really, our end of it in the beginning of it, like through the 2010 and 2015 period, was a lot of test stand evaluation. I built a test stand that could function in both open loop and closed loop test stands. So, so it was really helpful in evaluating durability and compressor mapping the turbochargers to validate what the design should be producing, and then see, does it really produce that?
Now, how many hours go into that? Because a while ago on a forum, I think I was looking at some compressor maps, and there was something on one of the forums. Somebody had mentioned that it takes hours and thousands of dollars to do testing like that to actually provide a compressor map for a turbo.
It really does.
Can you talk about how many hours?
I'll give you an example of why it takes a long time. Okay, you measure a charge air temperature in your car. Okay. You just look over at the intake air temperature channel, and it says 114, and you go, that's the temperature of the air. Yeah. It wasn't the temperature of the air. And at what RPM and at what flow rate was that the temperature of the air? Your car went from 2,000 RPM to 6,000 RPM in 2 seconds. At what point was it 114 degrees Fahrenheit? Yeah. Okay. So you can't really develop the answers to the engineering questions based on that sort of rapid transient data. Right. So you make a compressor map, like a speed line on a compressor map, you might consider that to have like a dozen points, where at each one of those points on the compressor map, you had that turbocharger operating at that flow rate and pressure ratio and speed at that, not quivering, just steady state at that point for maybe 10, 15 minutes. So you've got to change all the airflow rate and the temperatures on the burner and everything to get to that operating point, and then you got to maintain that. And in some cases that might mean that, like if you're at the top of the compressor map, you might have that thing running at a 4.5:1 pressure ratio for over 2 hours to get that high speed line. Wow. To collect that data for that high speed line. Yeah. Because you have to wait for the temperatures to stabilize. You have to wait for the air column to stabilize. You have a 12-foot long intake tube on the turbochargers, straight flow into the turbocharger with multiple sensor sets along the tube to measure the data for the air that's going in the turbo. And you have to hold it there long enough for all those numbers to stop changing. And you might realize that, wow, I've had it there for 3 minutes and it's changed, 7 degrees Fahrenheit in 3 minutes. But, over the next 30 seconds, it changed another 1.5 degrees. And over the next 30 seconds, it changed 1/4 degree. And then over the next second, it changed another 1/4 degree. And then over the next 30, and then they're like, wow, you had to just sit there and wait for it to stop changing and hold it at that point long enough to know that is in fact the correct data. And then you have to correct all of your flow data to standard temperature and pressure conditions. So where the temperature that you're operating in is different than the standard temperature and pressure. So you have to account for all that at the same time. So making a map can be very complicated. It's a very technical thing to do. And generally speaking, it's an iterative process to go back from simulations to test stand, simulations to test stand to validate that. So it does take a long time.
It takes a long time and it costs a lot of money.
It does. You spend a lot of money on it.
Do you have any situations where turbo maybe blows up?
Yeah, you'll consume turbochargers.
Oh, okay.
Yeah, you can consume turbochargers doing this, especially as you're trying to operate near the surge line, because this flow becomes unstable as you're getting towards the left-hand side of the compressor map. Right. So trying to get accurate mapping right next to the map is your riskiest part, because if it hiccups or gets unstable and the pressure starts to wonk because it's in the surge, that can snap shafts, that can cause a lot of problems.
So
And you break the turbo on the stand. Now you've done a terrible thing because now there's oil in everything.
yeah.
You have to take a lot of things apart and clean them and stuff. So
Do you do this for all your turbos?
you do validation for all the compressor arrows. Now every individual turbo, like say I'm gonna have a Subaru compressor housing versus that Evo compressor housing that rotates in the opposite direction. Mm-hmm. I don't have to make a whole new compressor map because it turns the other direction.
Got you.
Okay. So there's a lot of universal application to the map data, and we do post maps for like big differences in compressor cover. So like when you go from the X2C to the X3C to the 4C or 5C compressor cover, that can actually have some pretty significant changes to the map. So you have to test all of those. You have to test them all.
Sometimes it's hard to find some of these compressor maps for some of these turbos.
Well, if you go to, if you look at like the Borg Warner catalog, their PDF catalog, it's full of maps, all the turbos.
Borg Warner, yeah, they do.
Yeah. And if you go to the Garrett website and you look at all their product offering, for the most part, they're all there.
They're all there for every single one. Mm-hmm. So is it a sign? Is it a bad sign?
It's not always the right map. Okay. That's something I kind of giggle about sometimes because I look at it and I'm like, well, look, they got the same map posted for this model as they do this model, but it's different part number wheels.
Yeah.
So there's a little fudging that happens sometimes, even at the super manufacturer level that you see that get fudged sometimes. And
right.
I don't like that, but.
So if a turbo doesn't have a compressor map, how do you know what the flow capabilities of that turbo is?
You do have your data logs from the car, so you know what boost you were running
prior to purchasing.
Yeah. Oh, prior to purchasing. I don't know. Okay. You have to go to the forum and see what Billy Ray did on his 6266, I guess. And if he had a really good luck and you go do the same thing with him, then you can see if you have the same luck, I guess.
Right.
But having the maps and being able to compare and contrast two different models, like say, there's a 62 millimeter model, a 64 millimeter model, and for this particular snowmobile application or whatever, what your operating point is, then you can very directly compare the two operating points and see which one does it with a better speed match to the turbine wheel you want to use, which one gives you a little bit of a compressor efficiency advantage. And I think a lot of people don't think about when they're calculating their pressure ratio and how much boost they're going to run the turbo at. They always know how much boost they're going to run the turbo at, but a lot of times people don't know or think about what pressure ratio they're going to operate the turbo at. And you can have a boost pressure and not know the pressure ratio. And here's how you do it. You don't know what the inlet condition of the turbo was. So say like you got 997 application and the turbos point towards the front and the intake comes up behind the motor and behind the cooling system.
Right.
And it's kind of restrictive. Okay. So you might think, oh, well, the air gets there and I'm making 1,300 horsepower. I'll put bigger turbos on and I'll run 1,800 horsepower.
Right.
And you put the 1,800 horsepower turbos on there and it still makes 1,300 horsepower and you're mad. Okay. But then you call me and I go, well, hey, what was the vacuum in the inlet pipe? Can we put a sensor there? Well, I don't know, man. I'm just so mad right now. And I was like, well, we can maybe get less mad if we fix it, right? So let's figure it out. Let's fix it. Okay. So humor me. I'm just a dumb old Texas hick. So just humor me and just put a pressure sensor, about 4 inches away from the front of the turbocharger. Let's collect that data too. I said it was 83 kPa, Robert. What's that mean? I said, that's bad. Okay, you get a few PSI of vacuum in that charge pipe, and you thought you were running at a 4-to-1 pressure ratio, but you're actually operating at a 4.5-to-1 pressure ratio because you have too much inlet restriction. So you can see how well a turbo discharger has an ability to deal with an inlet restriction also by looking at the map. So if you're plotting your operating point on the compressor map and there's a lot of map above where you're at, well, then you have an ability to deal with a lot of inlet restriction, a filter, a sort of a restricted charge pipe, and the compressor will still perform at a higher pressure ratio. So there's a lot of information you can get from a compressor map, not just like how much will it flow, not just the pound per minute flow rate or the CFM flow rate, but how it will work when things change. And we do a lot of support for hill climb guys, like for Pikes Peak, my buddy Shane Tecklenburg does a lot of Pikes Peak cars, and that's a little bit more of a complicated application because you change elevation so much. You might have 10,000 feet 7,000 feet of elevation change, depending on what they're doing with the car. Snowmobiles, the same thing. You know, you might have guys that live at 3,000 feet, but when they take their snowmobile trip, they go to 7,000 feet.
Yeah.
And, you know, and it changes what the turbo can do or can't do without exploding. You know, sometimes a turbocharger, if you're telling it to hit this charge pressure and you have the wastegate and the control system set up such to achieve that regardless of anything with no safeties in place, it'll just keep the wastegate shut and the turbo will just try its little butt off to hit that mark. Well, maybe that means it spun faster than it was strong enough to spin. You know, everything that spins in a circle has a limit to how fast it can spin in that circle before it explodes.
Yeah.
Yeah.
Right.
So, and you have to consider this, you know, and that's what I don't like about turbo class racing, because the only way you can get a 62.9 millimeter compressor wheel to flow more is to spin it faster.
Right.
And if he's spinning his 10% faster than the red line, I'm going to spin mine 15% faster than the red line, right? And then as soon as he figures out I'm doing that, he's going to spin his 20% faster than the red line, right? And we're really just trying to see who will go close, and it's like playing chicken, you know? Who's going to go close enough to it to blow it up, but not hopefully not be the guy that blows it up.
Yeah.
Yeah, and that's why you're starting to see people have a little bit more concern for the safety. And I think World Cup this year is requiring cross bolts for turbine outlets, which is a great idea. I think I have an example of
cross bolts.
Yeah. This is a turbocharger that went way too fast right here. Okay.
Yeah, I saw that when I was setting up.
So when it goes way too fast, it just splits in the middle. You see how that's kind of right through the middle of the hub of the wheel. Okay. And you typically will see it break into three pieces when it's a RPM related problem, because you just kind of make three equal pieces out of it when it breaks.
What?
And you don't want those pieces to go out that little shorty exhaust pipe and right into that lady's face.
Yeah.
That just happens to be standing next to the car. Okay. So what's happening now is you're starting to see people implement bolts in the downpipe across the outlet pipe.
Does that restrict anything?
It does. It does restrict it a little bit. And you kind of have to plan for it if you want to optimize for that. And people will adapt. It won't be a problem. But the rule is, I think, within 3 inches of the turbine outlet, you have to have two arresting bars across it, bolts or Xona's a tile starting to make a discharge flange that has the parts made into it, and that's a high strength Inconel flange basically.
Right.
So you make your downpipe with that flange at the top. At the top,
yeah. Right. So this is going to be a requirement.
So you can see how, it is. Yeah, you see why it's so important. This housing is a tile V-band housing, and it's made out of a super alloy, a high nickel super alloy, and you can see that even though this exploded to the point where it looks like this. If you look at the outside of the turbocharger, none of the pieces left the turbocharger. The closest you get right here is it did kind of crack it open right there, but the pieces didn't escape. So that's called a containment success, really. Okay, and you can see by looking at the cartridge. I think I got the cartridge right in reach.
It's nice when you have the turbos just sitting right here.
So yeah, I got turbos all over the place here. So you can see what happened there. It's not that it just got broke off sideways because like a valve went through it or something. It actually just split off into kind of 3 pieces. And that's the nub is what's left, you know. Damn. And you don't want those pieces to go out the tailpipe. You don't want the pieces to blast out the side of the housing. So it's really an important thing. This is really, you might think, oh, that looks terrible, Robert. Why would you be proud of that? I'm proud of that because the pieces stayed inside.
Yeah.
Okay. If you get to, if I say this is okay to run this at 130,000 RPM and then you run it at 170,000 RPM, this is what happens. But the pieces stayed inside.
Right.
So I'm proud of myself. You know, I'm not ashamed that it broke. I'm surprised they don't all break, really, because I've met some of you guys that use these turbos. Okay, yeah, you know, I'm really more surprised that they're not all broken than I am that some of them break sometimes. But when you can have something just this catastrophic happen and the parts stay inside the turbocharger, that's a big benefit.
And what is that turbo rated power wise?
This was this is like a 64 millimeter turbocharger or 68 millimeter turbocharger, so somewhere around 800 horsepower.
Wow. What do you think he was making when that happened?
More than that. Yeah, more than that. Yeah.
Jeez.
Yeah. That's a pretty cool example of the containment.
When you're going through your catalog of turbos, right? How do you guys pretty much classify your turbo sizes?
We're in the process of we're in a changeover phase right now. Okay, when we launched Xona Rotor, the first two digits of the number were representing the recommended max flow rate for the compressor in pound per minute. So when we have something like that turbocharger at 95 69S, the 95 meant that we would like you to operate that at 95 pounds or so, and not much more than that. They will flow a little bit. They'll flow more than that. But you gotta put the yellow line somewhere, and the red line has to be on the other side of that, right? So, but people figured that out, and they started realizing that our 95 pound a minute will flow 102 pounds, and before you know it, things like this are.
So it makes it easier.
So we kind of decided that when we did this last round of aerodynamic updates and strength updates for the parts, that we would go to a more conventional method of naming the turbochargers. So now you see, instead of it saying XR9569S, the new 2024 versions of that would be called an XR, and then the next letter would tell you which compressor arrow it has. So it would be an XRC or an XRE or an XRA, depending on which compressor wheel arrow it has. Okay, and then the next two digits would be the compressor wheel inducer diameter, and then the next two digits would be the turbine wheel exducer diameter.
It's like precision, right?
So similar, the same millimeter notation that Turbine and Precision use.
So what was the reason for the switch? Because aside from just the people,
we weren't going to convert the world over to it, and it gets complicated when people think they have a 95 millimeter turbo, or I have an XR 5757S, and people go, "Is that a 57 millimeter turbo?" You're like, "No, it's 53 millimeter turbo." Oh, makes perfect sense, doesn't it? So it just, I ultimately just got tired of talking about it, so I give in. It's millimeter now, and all the 2024 models that are getting released and updated for 2024, they're all in millimeter format.
I'm not gonna lie, I actually like the way you guys have it though, because it kind of makes it easier for you to kind of know where your turbo is gonna flow at.
Well, that's why we did it that way. It was a nice thing, and we didn't release the maps at that point. So telling people what the flow rate was to us was a pretty important thing,
right?
Okay, but now we're releasing our maps. So if you want to look at what our 6868 does, it doesn't need to be in the name. It doesn't need to say, it doesn't need to say 88 pound a minute. You just can know, you just can look at the map to see what the performance characteristics are. And then it turns out a lot of people were really interested in what the compressor wheel inducer diameter is in the model name of the turbocharger, because people need to shop for the size that they need to run.
Right.
And a lot of times, it's like, hey, everybody that's going to run this Saturday has to have a 63 millimeter turbo, or everybody that's going to run at this event has to have a 76 millimeter turbo.
For classes,
Yeah. So, so you'd have a lot of people call you and go, which one of your turbochargers is going to fit this class?
Yeah.
And, it's just simpler, I think, to have millimeter.
I mean, that makes sense. That makes a lot of sense that you were able to kind of like, I don't want to say give in, but it makes a lot of sense.
It's giving in, because I wanted to use pound per minute in millimeter, and we have for a long time. And it was really effective, because if you're talking about turbochargers in general and you're kind of new to turbochargers, it's kind of easy to look at Xona Rotor turbochargers and go, oh, a 5757, if it says it's 57 pound a minute, then I should be able to make over 550 wheel horsepower with that when it's maxed out.
Right.
You just know that instantly just by looking at the name of it.
Right.
So if you knew that much about the turbo, how the naming nomenclature, how the convention went, then you knew a lot about what to expect out of the turbocharger.
Right.
And with millimeter, you know a lot less about what to expect out of the turbocharger, but you do know how it's going to tech. Okay,
right.
which
seems to be more important,
equally important, if not more important in a lot of cases. So,
now with the flow, with like the pounds per minute, right, that you guys have as a turbocharger classification, does that mean that the turbo is most efficient at that number, Or is that what it can flow to?
With the old nomenclature where it was that we gave a pound minute rating,
Yes.
we considered that the safe steady state operating point.
Okay.
So if you wanted to operate it at that flow rate at like approximately a 3 or 3.5 1 pressure ratio, you could set it at that operating point and just leave it there like an airplane or a boat. Okay. So, think about it. Like you don't drive an airplane or a boat the same way you do a car. Car is traffic. We're going to slow down and turn. We don't really do that with boats the same way. We're going to head east at this heading.
Yeah.
And I want 3/4 throttle. I want 3/4 power. I want full power. And when we go to boat, we go to full power. We're going to do it for just like 6 seconds like we do in a car? No.
Yeah.
No, man. The other side of the lake's way the hell over there, man. We're going to do this for 10 minutes. You know what I mean? So when you talk about steady state operation of the turbocharger, that's what those first pound per minute ratings from Xona were. They were really a safe, steady state operating point for the turbocharger.
Safe, steady state operating point. Now, can you tell where your turbo would be at, like on a compressor map based on whatever you're running, based on boost?
You can. You can if you want to assume that your compressor inlet pressure is ambient. Okay. Then you would say I'm going to run 30. Say I'm going to run 14 pounds of boost. Okay. So and let's just assume. Let's say I'm going to run 15 pounds of boost, and let's consider ambient to be also 15 pounds, 14.7, 14.5, depends on your altitude. But let's just say ambient's 15 psi, and we're going to run 15 psi of boost. Okay, so what I'm going to do to get the pressure ratio is I'm going to consider the ratio of the absolute outlet pressure to the absolute inlet pressure. So what would that be in this case? The absolute outlet pressure would be 30. Because the outlet pressure has the 15 pounds of boost that I made, but it also is pumping the 15 pounds of boost into a room that already has 15 pounds of ambient pressure in it. So the absolute pressure of the compressor outlet is 30 psi.
Right.
And now if I'm going to go check the pressure at the inlet of the turbo, I don't even have a pipe on it. I'm just sucking in the air from this room. I'm going to assume it's at ambient.
Right.
Well, we already stated the ambient was going to be 15 pounds. So I'm going to take the 30, I'm going to divide it by the 15, and what am I going to get? A pressure ratio of 2.
Right.
So I'm going to go, now I'm operating on this line that says PR2 on the compressor map, okay? And if I'm making 300 horsepower, okay, like I just dynoed it, or I just realized my car weighs 3,000 pounds and it just ran X mile an hour at the track, and I do a little calculation and it's going to tell me I'm making 300 horsepower. Now I'm going to go on the X-axis and I'm going to look for about where 30 pound a minute is. Okay,
right.
Because with a pound a minute of airflow, generally speaking, on a modern engine, you can make about 10 wheel horsepower. Really rough approximation. Okay,
so you times it by 10 basically.
So you times it by 10 basically. So if you made 300 horsepower, you go to the 30 pound a minute part on the X-axis. Now you're going to find out where do those two lines cross.
Right.
The 2-to-1 pressure ratio and the 30 pounds a minute, where does that cross? Well, that's about where I'm at. And if you had a tach on your turbocharger and you made note of the number of the RPM of the turbocharger, when you look at the map, you should see a speed line that is somewhere near your operating point, and the number that was on your turbo tach should be really close to either the number that's just above or just below your operating point. You should, if your operating point's not on a line, and it won't be, it's between two lines, you'll see that your speed, your shaft speed, is between those two RPM lines. The RPM lines are the curvy lines.
Right.
And then there's islandy lines in the middle, and that just tells you what your compressor efficiency is. That means for, like, if I put in 100 units of work, I will get 77 units of work back out of it on the compression side.
Got you. Okay, so you basically just broke down how you how you would determine what turbo you need for your setup.
That is level 1 analysis of what a compressor map does, and how do you figure out where you're at and where you're operating at, and what does a compressor map mean to you.
Right. Now, what if you were doing this? You mentioned before if you had a 300 horsepower, right? Now, is this NA or this is with the turbo application?
Well, if you're trying to like take if you're trying to look at a car that you know how it's operating and have data on the car, like you have the car weight and the horsepower and the boost pressure they're at, and you're trying to look at the map to see where it's running,
right.
well, then it's wheel horsepower is what I'm talking about. Okay. If you're trying to pick a turbo based on stuff you don't know yet, you don't have a data set yet, then you kind of do the same problem, but from the opposite direction. Okay. So you say, hey, I want a 800 horsepower 4-cylinder. Okay. So, I know generally speaking, other people that make 800 horsepower on 4-cylinders operate at about 40 pounds of boost. Okay. So what is the pressure ratio for 40 pounds of boost? Okay. So it's going to be 40 pounds of boost plus 15 psi, so 55 divided by 15, so that comes out to like 4-to-1 or something like that.
Something like that.
Okay, so that's the pressure ratio that you're at. So that's the left right line that you're going to be at. So now you're shopping compressor maps. Okay, I want something that works really good at 4-to-1 pressure ratio and about 80 pounds a minute. So now you're looking at maps going, well, which one has the best operating point for that pressure ratio, 4-to-1 pressure ratio, and 80 pounds a minute. And if you're torn between these two models, it makes it pretty easy. You go, well, look, this one has 73% at that operating point, and this one has 68% at that operating point. Right. I'm going to go with the one that has 73%, unless I have some other reason not to.
Yeah. Without us even having a chart or anything to look at.
I use my hands.
Yeah, I was thinking about like showing, like kind of trying to, I guess, show it, but I don't know.
I almost brought a little dry erase board to draw on, but I figured we'd just talk about it.
Yeah, I mean, it was pretty. I'll put something up on the screen. I'll have to do some editing for this, just so you guys can kind of see it.
Well, if anybody's watching this program and they think they understood or they have a question about that, and they're looking at their car and they're looking at their application and they want advice, because they think they understood what I said, but they're not sure. All they have to do is call me. I'll probably get on the phone and I'll probably spend 15 minutes talking to you about it if you're a nice guy, so, and maybe you'll want to buy something. I don't know, but
yeah, definitely will probably end up buying something. It's always the people that help that you end up want to work with,
And that's the bottom line. That's really, I think, the secret to the success that I've had my whole career is that I've always just tried to have a real focus on actually helping somebody. Yeah. And if somebody is belligerent or super mad, and there's nothing you could do to make them not be super belligerent or mad, then you're never going to help that guy. It's never going to be a successful situation. And those are the people that bum me out the most, because it's like, man, I could have got you there, man. Yeah. But you're too hung up on being mad, Yeah. And the turbos are just turbos, man. They don't mean that much, I always say, if you have an actual turbo emergency, please hang up and dial 911. These are just turbochargers. At the end of the day, it's not your child, it's not your favorite dog, it's it's not your wife being sick. It's nothing like that, man. These are just cars that we spend way too much money on, and but this is our weakness. So it's you have an addiction, and sometimes you could have healthy addictions, and I think cars are probably a healthy addiction.
They are, depending on who you're married to also. But. So now one of the things with turbos, since you mentioned people blowing them up before, is oiling, right? Now you have a pretty much kind of different technology that you guys do. I don't want to say it's different, but you guys are one of the companies that implement water cooling into your turbos, right? So can you kind of explain why it's probably better to run a water cooled setup as opposed to just oil?
Yeah, for sure. If you are a drag race application,
okay,
and you trailer to the track, and your golf cart pushes you up to the line, and you fire the car up just 3 minutes before you do your hit, you don't need water cooling. Okay. You really don't. Okay. It's gonna almost get up to temperature by the time you turn it off. Okay. So the water cooling is not really going to be there for you for any real big benefit. Okay. But if you're trying to get from the bottom of Pikes Peak to the top of Pikes Peak, okay, and we want to talk more about the steady state style of operating, okay? And then water cooling is a big part of that, man. Okay, because particularly on your turbine side ball bearing inner race, okay, because everything gets weaker as it gets hotter. Okay.
True.
Okay, so bearing material is the same way. The strength and the hardness and the toughness of bearing material reduces as the temperature goes up, okay? So say I have a rally car or Pikes Peak climb car that is on anti-lag virtually the whole 20 minutes for the section. Okay. So the turbine wheel is glowing red. The turbine housing is glowing red. And about a 1/4 inch away from that glowing red turbine wheel is the ball bearing. And you don't want the ball bearing to really get above a certain temperature. Like you'd like your inner race temperature to, probably stay in a 300 Fahrenheit range, okay? Which means your shaft should have no discoloration on it. When you take the bearing off the shaft, the area underneath that shaft should still just be a chrome steel color. It shouldn't have any purple or brown to it. Yeah, okay. If you take the turbocharger apart and it's purple and blue up to the bearing, and then on the other side of the bearing it's purple and blue, well then that stuff was glowing a dull color at some point while it was running. Okay. And that is that might be what you have to do to win. Okay. But you have to understand that when you're doing that, and you're the one that decided to do that. Okay. And that's going to be, you're going to burn your candle a little faster when you do that. Your bearing material is going to not last as long, and your longevity out of the turbocharger is not going to be as good as if you kept the temperatures lower.
This episode of the Street Alpha Podcast is brought to you by Race Motive. Bring your car from the streets to the track at Race Motive Racing events in 2024. From Pocono Raceway, Maryland International Raceway, New Jersey Motorsports Park, and new this year, Maple Grove Raceway, Race Motive brings you top-tier roll racing events. Their Olympic-style grading system ensures precise measurements for fair competition. From the high-friction NASCAR surface at Pocono to fully prepped drag strips, every race promises excitement and fairness. So bring yourself and your car and use Street Alpha Pod for 10% off all tickets, whether you spectate or race at racemotive.com. Don't miss your chance to race with the best. Okay.
So water cooling. If you're gonna run the car at full power long enough to open the thermostat, then you probably want to water cool. Okay. But if you are just drag racing or just doing a half-mile hit or something like that, it's less critical.
Okay. Is there any data that pretty much, or it's just like something that you kind of came up with that you were like, oh, well, if you add water into this, it's going to cool it down faster? Or is
no, we put thermocouples into bearing housings, and put open tip thermocouples directly into turbochargers, measure oil drain, measure the temperature of the oil coming out of the drain. Okay. This is a really good indicator for how hot the bearings were. Okay. If the oil coming out of the drain tube is at almost 400 degrees Fahrenheit, well, damn. Okay.
That's okay.
Okay. And that's as simple as just adding an open tip thermocouple in the drain tube near the turbocharger, and just see what the temperature of that oil was that's coming off of there. Okay. I put thermocouples on and journal bearing turbochargers into the bearing housing right next to the thrust bearing, so that the oil that got slung onto the thermocouple came off of the high pressure side of the thrust bearing, and develop ramp styles and specifications for my thrust bearings based on what gives me the least amount of temperature rise on the bearings. And the higher you turn up the boost pressure on a journal bearing turbocharger, the higher that thrust bearing temperature is going to get. And a lot of people, that's typically what you're going to break on a journal bearing turbocharger, is you're going to smoke that thrust bearing.
On a journal bearing, right.
On a journal bearing turbocharger. On a journal bearing turbocharger, and I'm kind of jumping from water cooling over to ball bearing versus journal bearing, but on a journal bearing turbocharger, you can't interrupt the flow of oil to the place that's requiring lubrication. So you can't interrupt the oil flow to the ramps on the thrust. You can't interrupt the flow of oil to the journal bearings. Those things have to float on that oil.
Right.
Okay. So if you're not having pressurized oil film pumped into that surface, you got one stationary surface and another surface that's going about 1,000,000 miles an hour. Okay. So that's all cool and everything, as long as I got 250 degree Fahrenheit, 10W30 oil going through there at 30 PSI.
Yeah.
Those two things will not touch each other. Okay. But as soon as I launch the car and I have 2 degrees of forward 2 G's of forward acceleration, and the oil pickup sucks a little bit of air, and now I've got 30 pounds of oil pressure, but it's got bubbles in it. Okay. Now I don't float the bearing anymore.
Right.
Okay. Now the bearing is floating in bubbles, and shit don't float in bubbles. Okay. You only float if you're displacing, if you're displacing a liquid. Okay. You have to, if there's air there, then there's no way to float and keep the two pieces apart. They say that the ships even sink when methane bubbles come up out of the ocean. If you have a big tanker, and tanker will just disappear. They go, what the hell happened? Nothing could sink that damn tanker. Okay. And they find the tanker, and it's in the bottom of the ocean, and there's methane fields all around it. And what happened? Methane release came up, big bubbles come up out of the water, and this can actually sink a ship. You know, you can look up ships sinking in bubbles on YouTube. You'll be able to see videos of this.
I got to see that
Different
now.
universities do mock-ups of this in water tanks and stuff. It's a big field. Maritime technology is through the roof. Okay. So I want to talk about funding, maritime technology. They got funding. Okay.
What?
So you can't float in bubbles is the problem.
Okay.
So apply this lesson to the thrust bearing. If I'm going to pump bubbles to the thrust bearing, I'm not going to float my thrust bearing either. Okay. So you get the guys sometimes that are like, well, the turbo lasted one pass, you know? And I'm like, well, tell me what happened. Well, it was making 920 horsepower, man. And, you know, it took it, you know, I put the slicks on it, and man, it cut a 160 foot, and, you know, and I'm like, okay. That kind of explains why it's all melted together. Send me a data log of the motor, and it'll have the oil pressure on there. And if you're lucky, if you're sampling it at like 2000 hertz or more, because then you can actually see the bubbles. Okay. What? If you got a fast enough channel on your data logger, you can actually see the foam go past the sensor.
That's crazy.
On the oil pressure sensor. Yeah. So yeah, and you might have a log that you could go look on this on your own, where you launch your car really high. You look at your log for your best 60 foot ever. Okay. And then go look at your oil pressure channel, and then zoom up on it and verify how many samples.
So you have to zoom in, right? Okay.
Yeah. And if it's sampling at 1 hertz, then it's going to take 1 data point every second. You're not going to see the bubbles. Okay. So if your data stream is not collecting 2,000 samples a second, then you're not going to see 500 tiny little bubbles go by.
Right.
Okay.
Right,
you're going to get more of an average, whatever kind of temperature, pressure measurement. But if your sampling rate is, set it to high. If you want to see this phenomenon, set the sampling rate on your oil pressure channel as high as it'll go, and go launch your car, and then go look at your oil pressure channel, and you'll be surprised.
Dude, that's crazy.
Yeah. And people will go, well, my motor's fine. I was like, well, why'd the turbo go? The motor's fine. I said, the main bearing in your motor is like 40 turbocharger bearings worth of surface area. It wasn't enough bubbles to lose float there. Yeah. But it was enough bubbles to lose the float in the turbocharger.
So how do you prevent the bubbles from, like, is it something that's just
dry sump?
Okay, dry sump. Is that the only way?
Go to ball bearing. Floating ball bearings. Okay, ball bearings, you're transmitting the force not through a hydraulic layer. Okay, so in a ball bearing, the outer race touches the ball touches the inner race touches the shaft. There's a direct mechanical connection between the two. You've just got to keep it moist.
Keep it moist. Interesting.
Okay. Yeah. On a journal bearing, it's just got to be garden hose oil. Okay, on a journal bearing, you've got to have so much oil there that there's no bubbles, and it's constant, and it's always flooding through the bearing.
Is that part of the reason why there's like shaft play on the journal bearing?
Yes, sir. Exactly.
That little cushion is basically for
that's
the oil?
Space that's supposed to fill up with your oil pressure when the motor's running. Yeah. And you have that in a ball bearing too. Okay. People sometimes overlook that, but you have that in a ball bearing, but it doesn't come from where you think it comes from. It doesn't come from between the shaft and the bearing. The bearing is in a casing, and now the casing floats in the bearing housing. Okay, and you have to have this oil film there because you have to dampen these high frequency vibrations, or else they'll turn into high cycle fatigue failures of your parts. So you have to take all these little peaky vibration things out of the rotor group, or else you're going to break things for a different reason. Okay, but a ball bearing, the balls are inside of a cartridge, and it looks like just a little sleeve. It's just, it looks like a piston pin almost is what the ball bearing cartridge looks like from the outside. Okay. It's just a short little piece of metal, and the balls are inside that. Okay. But that has wiggle room in the bearing housing, and the oil comes through the bearing housing, fills up that cavity, goes in through the space between the bearing housing and the bearing, and into the ball bearing through little ports that are drilled in the outside of the casing. And then those little ports spray the oil on the balls. Okay. Most of the oil that flow that you need for a ball bearing turbocharger is to float the casing. Okay.
Which is why there's still minimal shaft play.
There's still some flash play on a ball bearing turbocharger. Yeah. Yeah. And I'm not big on people trying to buy and sell used turbochargers, but you'll see people say, I've got this turbocharger, just pull it off. It's got 0 shaft play. It's like, well, that's bad.
Well, shaft play, not, what is it called?
If it doesn't have any axial or radial shaft play,
yes.
then you've got pieces of rod bearing packing up that space, and that's why it doesn't have any free play. It's supposed to like a normal T4 journal bearing turbocharger should have about 25 thousandths worth of radial free play, something in that range, depending on the model and the brand and the way it's set up.
Okay.
And then maybe 1,000ths of axial free play, maybe 7/10 thousandths of axial free play. Maybe on a great big S400, you might have more like 1.5 or 2 thousandths of axial free play. But you're going to have free play because the oil has to go through there. If the oil doesn't go through that free play, then it's not floating those two parts away from each other. So you have to remember on a journal bearing turbocharger, when you have an external force that comes in, you're actually transmitting the force through the layer of oil.
Yeah.
Okay. So it's kind of like saying where your brakes work. It's hydraulically supported, whereas in a ball bearing turbo, it's mechanically supported directly. One part touches another part, touches another part, touches another part. But then you get the damping on the whole outside of the bearing cartridge, on the ball bearing cartridge. So you still have to damp, but you don't lubricate the balls the same way. The requirement for lubrication on the balls is not the same. See, the damping chamber on the outside of the ball bearing cartridge can have bubbles in it. That's fine. It still performs its damping feature. Okay. It's not the same requirement.
Right.
Plus, there's a huge amount of surface area between the outside of the bearing casing and the bore that is in the bearing housing. So you have a couple of bubbles, go through there.
Yeah.
It's no effect. Okay. But but those same bubbles that have no effect on the outside of a ball bearing casing, as far as damping and supporting the bearing casing, could kill a thrust bearing on a journal bearing turbocharger. So this is why you have journal bearing turbochargers. I like to use an analogy that's the canary in a coal mine. And I've said that a long time, and I've only recently started to realize that nobody knows what I'm talking about anymore. I say it, so getting older. But my grandfather was born in Pennsylvania, and his dad was a coal miner. He mined some coal too, and so I'm very familiar with the idea of taking a canary with you when you go into the mine. Okay, why would you do that? It's not just because you need to do something fruity that wastes your time, right? There's got to be some real reason that you need a canary with you, right? Yeah. Okay, well the canary's heart pumps really fast and it can't breathe very much air in one breath. Okay, and when you go deep into the mine, if the air starts to suck or starts to have a lot of carbon monoxide or methane or whatever is in the air, the canary's going to pass out. So as long as your canary's singing, so if you're mining, if you're deep in a tunnel in a mine, you want to hear your birds. Okay, but as soon as you stop hearing your birds, you need to get out of there, man. You need to get out of there because the air's bad. Okay, so you need something is to be the first thing to go, right?
Right.
So you take a weak link with you so that when the weak link breaks, you know that you're in trouble. Okay, that's the analogy. That's where the canary in a coal mine idea. That's where the saying comes from. This is the weak link that's going to tell me I have some trouble coming.
Yeah.
Okay. So in a journal bearing turbocharger on a race car, your thrust bearing is your canary in the coal mine. That is the first thing that's going to go on the whole system as a result of inadequate lubrication.
Now,
and that could just be that one 1.160 foot that you did.
Yeah.
It could just been that one time.
Right. The air bubbles.
Yeah. I just took it out. Did one hit, and now it's messed up. Well, it could happen.
Now
it could happen.
Okay, so now you said so much information. So basically, the journal bearing is not good for drag racing applications, you're saying?
It has that one weakness, doesn't it? Okay.
Yeah.
Now, if you're running 1/760 foot times, then you really don't have this problem as much. Okay. But as soon as you put slicks all the way around and you're launching at 7,500 on a two-step,
yeah,
and you're cutting those low 60 foots,
It's time to go ball bearing.
now is when you have this weakness. Now is when you have this susceptibility to having bubbles or oil filtration problems. Unless you have a dry sump, okay? Because then obviously the oil that's going to the motor is not even just the oil that's slung off the crankshaft. It's the motor that slung off the crankshaft, got sucked back over to the tank.
Yeah.
Then the pump took it out. Fresh, good, clean oil with no bubbles in it gets pumped back to the motor, okay?
Yeah.
Regardless of whether there's any pickup problems at all, because the pump is not dependent on having a continuous pickup anymore. The pump is taking it out of the tank, and you got 1.5 gallons in the tank.
Right.
So no problem, So dry sump cars, you don't see it. You used to see this a lot when Evos were really popular on road courses, okay?
Yeah.
Okay, the Evo pan is on the opposite side of the DSM pan in my head right now. I think it's when you take a hard right-hander in an Evo. But the oil pickup is in the deep end of the pan, okay?
Yeah.
And if you turn really hard
Yeah, it's right.
away from
I
it,
think it's right.
okay, away from that, now all the oil rushes up to the shallow side of the pan, and the pickup's hanging out down there, but it doesn't have no oil buddies hanging out with him. So he starts pumping air. You burn motors and turbochargers on road course cars by turning really hard. So the same way that you have a limitation on forward acceleration G with journal bearing cars and non-dry sump oil systems, you have the same limitation laterally on road course cars that have 275 Pirelli P0s all the way around that are taking 2G left turns.
Right.
So you just have this problem, because what are we trying to do? We're making a machine that requires lubrication, and then now we're going to take the limits of the machine all the way past the limits of the machine, and we're going to see what happens. And these are the friends you make along the way.
Would an Accusump combat that?
I don't think Accusump is really going to be faster acting enough. In my experience, no.
Just curious.
Okay.
People have Accusumps.
I mean, if you were like say you're a hill climb guy and your truck just got stuck like this, and it's there for 10 seconds like this while you try to get it unstuck, the Accusump can bleed off and give you get by oil.
Okay.
In the meantime, okay, but the Accusump, what I was talking about sampling rate on the oil, the Accusump is not working at 20k hertz.
Okay, so it's not producing.
No, and it's not going to displace the foam out that's in the main galley either. Yeah.
True.
The foam's still going to be there.
So now that you mentioned all of this oil, right? The water cooling side of it. Do you have to run separate lines to be able to cool the turbo? Like, where's that coming from? Is that being plugged into
radiator coolant?
Right. So you have to tap into that system to basically provide water into there.
So the coolant will come out of one part of the cooling system that is high pressure, and then it will go back into another part of the cooling system that's low pressure. So sometimes you use the inlet side of the inner radiator and the outlet side of the radiator, or depends on there's enough different ways to do it that there's not really a standard way to do it.
Right.
And cars are configured so differently, and you usually want to run the shortest lines you can and keep it simple. And in every factory designed turbocharger car that I can think of is water cooled, because what are they designing the car for? Steady state, operation. So they're all water cooled. So if you're just taking a car that already came with a turbocharger and you're putting you're upgrading the turbocharger and enlarging the power output of the motor, usually just use the same coolant sources.
Right.
You might just be changing the hardware to connect with.
Well, it's like on the BMWs, they have like heat exchanger, and then they have like the water in the intercooler to cool and everything. So
You would not want to use the charge air cooler liquid. Okay, because you're gonna be skunking up the charge air cooler liquid with a bunch of temperature that you don't want.
Right.
You want to keep charge air system separate totally from your turbocharger cooling system. And on cars that are like, say you got air cooled cars. Okay. Not as common today as it used to be. What do? I can run oil through the water jacket. You just run oil through the water jacket.
Interesting. So it's air cooled. Yeah.
So you don't have any radiator, right?
Yeah.
So what do you have? You probably have a lot of oil.
Yeah.
Okay. Like if you look at something like a 964 Porsche motor, I don't know how many gallons of oil is in that motor, but it's several gallons of oil, in a dry sump system. So you totally could just take another branch off of your pump system and run through your turbochargers and then back to the tank. and let the cooling system that's already present deal with the heat. Yeah.
Right, do the job. Okay.
If you're going to run the car long enough for the thermostat to open, then you're going to have a benefit from using water cooling for the turbocharger. And I want to talk about one other point to water cooling. Okay.
Yeah.
So, like I said, if you have a drag car, you can get away without it, right? Because you're pushing up to the lines. It's never really running long enough, et cetera, et cetera, et cetera. But what you do have in a drag car is, ball bearing turbochargers usually run with restrictors. There's not a lot of oil volume going through the turbocharger.
Okay.
So when you shut the car off, the turbocharger is now pretty hot and it has no oil going through it at all anymore.
Right.
So the oil that's in it can cook where it's sitting. It's not like running through.
Right.
When the oil was running through, it didn't stay there long enough to burn. It's kind of like that walk across the fire trick.
Yeah.
You're not going to stop in the middle of the fire and then talk to somebody. You're just going to get your ass across the fire.
Yeah.
So the oil going through an air-cooled turbocharger is the same problem. As long as it just gets in there and gets out of there, the oil's okay. It comes out at 350 degrees Fahrenheit, 400 degrees Fahrenheit, and then the oil cooling system deals with the rest of it. Okay. But as soon as you don't have the oil flow going through the turbocharger anymore and the oil's just sitting there, that's just like that one piece of bacon you put on a frying pan, but then you picked up the phone and you turn it back around, it's like it's not butter anymore. It's just black charcoal. Yeah. So you take apart air-cooled drag race turbochargers that people had on their car for a couple of years, and it's usually just like a crusted, carbon, burned up, just mess on the inside. You have to soak those bearing housings in lye for hours to break that carbon down and get it out of there if you're going to try to reuse those parts. You have to do that just to inspect and measure the parts to see if you can reuse them. So it's kind of a total pain in the ass.
So what if you're doing like a twin turbo setup though?
If it's mine, we're water cooling.
Water cooling. Mm-hmm. Okay.
So if you're running it long enough for the thermostat to open and need to have fans come on, a radiator, then you're going to benefit from having water cooled turbocharger also. And you might not see it like the first 18 months of running the car, okay?
Yeah.
But you get into that second or third year running the car, you're like, why is this thing so loud? Well, that damping chamber around the ball cartridge that I'm talking about, it doesn't have oil going through it anymore. It's just all carbon. And it's not floating in a damping chamber anymore. It's just frozen there. Okay, so now every little vibration that happens directly gets transmitted to the rest of the system, and the turbo gets loud. Along with little pieces of that carbon breaking off and then the balls having to roll over them.
Right.
Okay. And that puts little pits in the races. And it used to put pits in the balls when they were metal balls, but now they're ceramic balls. So it doesn't pit the ball anymore, but it does pit the races. So when you hear somebody's turbocharger, like say they're idling and they turn the motor off and that sounds like an old skateboard wheel.
Yeah.
Okay, it's got some carbon on the balls at some point or another. And it's made little pits in the bearing races. Carbon turns into a diamond. Okay, so the edges of carbon are sharp and hard. So it's one of the things that can scar the bearing race and make a little mark. And then every time the ball hits that mark, it makes a noise and it makes a vibration. And all the vibrations add up to cycle fatigue, and should have used water.
Should have used water at that point.
or just buy another $4,500 worth of turbos. It's up. It's either way.
It's up to you. Whatever route you
spend $400 making some water lines, or you spend another $4,000 buying new turbos in 2 years. But if you buy new turbos every 2 years anyway, why do you care? You know what I mean? It's not like used turbos are worth much.
That's true.
You know what I mean?
Yeah.
Like if you got some turbos that have the tile stainless steel housings on them, you might just get away with just buying new super cores and using the same exhaust housings, for more than one set of turbochargers. But, generally speaking, as a race car, you're not going to get away with just using the same turbochargers over and over again, year after year after year. You're going to break them, you're going to bend them, you're going to stretch them, you're going to suck some stuff in.
Right. It's part
the tips are going to melt off the turbine blades. It's never a surprise to me when turbochargers are broken. And I've said that before. I even said it before 5 minutes ago. But people will call you up and say, I just can't believe this broke. And I'm like, I'm pretty sure you could break a anvil, bro, if you wanted to. Okay. I'm not surprised it broke. So let's just see what we can do to help you. Okay.
So for those customers, right? So you spoke about pretty much how the importance of oil is, right? To kind of keep everything flowing. Now, how important is it to prime your turbo?
Ball bearing, it's not so relevant. Okay, because it had enough residual oil in it to deal with the first hour of operating, probably. Okay, I'll tell you a little story. We had a guy that was a Porsche customer, road course customer. We sent the turbos to the guy. They put him on a car, tuned the car, dyno tuned the car, road tuned the car, delivered the car to the customer. Customer took the car to the road course for the first trip for the weekend.
Yeah.
And he does a 20-minute session. He goes back into the pits, has a sandwich, visits, talks to his buddies about how awesome his car is and stuff. He's back in the car and go to another 20-minute session. And then one of the turbochargers fails. Okay, just like rattling around, death rattle, just flopping around in there. And I'm like, oh, that sucks, dude. Sorry. Let me see what I can do to help you. Sends the turbos. He left the oil fittings on the top, okay, of the turbochargers. So I could see the fittings that he had on the turbochargers. And the turbo that broke, it was bone dry. I mean, like mummy, like sand dry, like just dehydrated fruit dry inside that turbocharger. So I'm like, this doesn't look like it was getting like any oil. It's weird. But how did this car run for dyno tuning, street tuning, the first 20-minute session, and part of the second 20-minute session without breaking? And so it's crazy. It's crazy. So I started looking. I'm like, there's a hole that's not complete somewhere because this turbo got no oil. And the fitting, the little fitting that somebody screwed into the top of the turbocharger, it was a restrictor fitting, like a tiny little orifice fitting. Like they're very common. But the drill bit had broke off at the bottom of it, and it didn't drill a hole all the way through it. So, so when they put the turbos on, the whole time it dyno tested, the whole time it street tested, the whole first 20-minute track session, that turbocharger only ever had the oil in it that was left over from balancing it when it was on the VSR balancer. And it lasted, I don't know, 20 dyno reps, a 20-minute road course session. It lasted like way longer than I would have expected it to last with no oil in it. So that just goes to show you, you don't need very much lubrication for the balls. They need to be damp, they need to be moist, but they don't need to be flooded with oil. And most of the oil that you run through a ball bearing turbocharger is not there to lubricate the turbocharger. It's just there to carry a little heat out so that the oil doesn't burn in place.
Now what about a journal bearing?
Journal bearing, you have a garden hose worth of oil going through it. So like a TD06 style turbo or a TO4 turbocharger, you have an unrestricted -4 line. So 110,007-inch diameter tube, 1/8-inch diameter tube, feeding straight engine oil to the turbocharger. Way less critical to have water cooling on an application like that because you literally have quarts of oil per minute going through the turbocharger. Where on a ball bearing, you might have 1 ounce of oil go through the turbocharger.
Well, in terms of priming, though, you still have to prime it.
Priming, yeah. Coming back to priming, journal bearing, yes, you're going to want to prime it.
Okay.
Yeah. So journal bearing, you're going to want to do something like pull the plug wires or pull the fuel pressure relay or the fuse or something. Let it crank until you see some oil pressure on the sender. So now that at least the pump's got a prime and there's some oil in the galleys, then you can go ahead and fire it because then within a matter of 2 or 3 seconds, oil will get to the turbocharger. If you're really worried about it and you're like, no, man, my turbo's really far away and I don't want to do it, you take the turbo line off the top of the turbocharger, pull the spark plugs out of the motor so the motor will turn over fast and crank it until oil comes out of that line. Then connect the line to the turbocharger, then put the plugs back in and then fire it. And then there's no way you could have dry started it.
Right.
Yeah.
So now how do you know if your turbo is getting too much oil? Because I know back in, even with the DSMs, they used to run, or I'm not sure if the Evo still do run restrictors on the turbo line. Is that still
the factory turbochargers they don't have an 1/8-inch feed for them, no. But also the thrust bearings are a lot smaller than the thrust bearings that I developed for the Evo turbos and the DSM turbochargers. So at the same time that we're modifying the thrust bearings, we're modifying the volume of oil going to the turbocharger too. And in the DSM and the Evo, factory-wise, you feed off the cylinder head.
Right.
So you're being the rooster in that case is when it comes to eating. You're letting all the hens eat first, and then if there's anything left, you'll eat some. Okay, that's how the turbocharger is oiled almost always on OEM applications. You see it in Subaru too. Our turbocharger is one of the last things to get oil. Subaru motor, we feed the mains, we feed the rods, we float the camshafts, and we lubricate the cam buckets, and then whatever's left over, we'll let the turbo have it.
Right.
But from the factory, they have very small turbochargers with little tiny bearings, and that is more or less an adequate amount of oil to do the job.
Yeah.
But as soon as you put a bigger turbocharger on that has stronger, heavier, larger surface area bearings that flow more oil, you need to also increase the volume of oil getting delivered to them. So like in the case of the Subaru, instead of feeding off the back of the cylinder head, we now feed off the main galley right at the front of the motor.
Okay.
So right where the idiot light normally goes, you'll take that plug out or the plug out in the back, and you take oil pressure right off the main galley. That way you have like 15 more pounds of oil pressure for the turbocharger. Same thing on the 4G63, the DSM, and the Evo. You journal bearing turbocharger applications for those cars, you feed directly off the oil filter housing. You plug the head feed. You don't use the head feed. You pull a plug out of the oil filter housing. And you take the oil directly out of the oil filter housing just after the pump. And that way you have an adequate amount of turbo lubrication. How do you know when you have too much oil pressure? Generally, it's not going to all go down the drain tube, and you're going to have like mosquito fogger, James Bond smoky thing going on.
Okay.
If you can't get it to go down the drain tube, you could be supplying too much oil. But you could also have a drain tube problem. You could always also have like a plug, a crankcase breather or something like that.
Yeah.
And you'll see that really common when the weather first starts to change, and you see more condensation in the catch cans and stuff like that. Well, you get that snotty catch can condensation stuff plugging up the vent, the filter on the catch can, and then what happens? All of a sudden, it's not a catch can; it's a pressure can.
Yeah,
and it's not venting anything, and then having that pressure in the crankcase, the pressure's trying to puff up the drain tube, and the oil's trying to gravity feed down the drain tube. So it just sits there and does this stuff,
right?
And you fill a turbocharger up with too much oil, and you'll leak. So if you're leaking oil out of your turbocharger, it's possible that you're delivering too much oil, but it's not the main reason that you're smoking. Usually you have a problem with your crankcase breather system, or you've bent or damaged the drain tube, or maybe you had a rubber hose section to your drain tube that started to delaminate because it was heater hose instead of oil hose, or something like that. Generally speaking, you have a problem like that. But if you just put something together and you don't know what's going to happen, and these are just the things you have to just debug when you first put everything together.
Okay.
And I do a lot of debugging with people like that. People get frustrated because they're like, I just spent all this money. I got a brand new motor. I got a brand new turbo. I got all this stuff and it's not working. And I was like, it's not working yet, bro. I mean, you don't just buy a puzzle from the store and throw it on the table and go, it's not right yet. You haven't put all the pieces together the right order yet. You'll get there. Come on, it's just a car, bro. I'll help you. I'll help you figure it out.
He seems like you speak to a lot of frustrated customers sometimes, huh?
Yes. This is a frustrating job. Not my job, but the job of building the car is a frustrating job. Okay. Yes. I don't mean my job is frustrating. That's not anybody's problem. I'm saying that when you want to build an 800 horsepower 4-cylinder, you have got your work cut out for you. Yeah. There's going to be a lot of frustrating days. And then say you want to get fancy and you want to low mount a turbocharger in the fog light hole in the front. You just set the game on expert, man. Okay. You just set the game on expert, man. And you're not an expert. Okay. But I'll talk to you about scavenge pump systems and how to set them up correctly and what sort of check valves to use and how much venting you need on your sump underneath your turbo. And that's right about when they go, what sump under the turbo? You could make life hard on yourself really quickly with car projects, but I always try to remind myself, just got to help somebody figure it out.
Yeah.
You're only helpful if you're actually helpful. So you got to listen to what they're saying, and you got to read between the lines, and you have a crystal ball. Got a great one, and just jump in there and help people figure it out. Really, is the only way to do it. And they're all different. People are all different for sure. So
no, 100%, especially with the type of work you're doing. So I completely understand a lot of factors, a lot of variations and stuff.
And very little engineering, on the consumer end of things. It's like, well, I read a forum, I saw a video, and I did the same thing.
Yeah.
Okay, good. You thought you did the same thing. It's a fine line of helping somebody learn something without being condescending or without insulting somebody. And people that will accept some constructive advice usually have their projects turn out better faster. You can't come into trying to build an 800 horsepower 4-cylinder with a chip on your shoulder thinking you know everything, unless this is your 10th one that you've built. then you could walk into it with a chip on your shoulder. Okay. But, if this is the first time you've ever tried to do this, then you need to speak less and listen more.
Yep. A lot of people need to do that. A lot.
I try to remind myself all the time. Man. I learn more every day.
Yeah.
Yeah.
You got to be humble when it comes to this and always willing to learn. Now, can we talk about some of the designs that you have in terms of like the wheel and how that has helped advance turbo technology for the most part?
The advent of the Xona Rotor UHF turbine wheel was a pretty substantial thing. Okay. It really did change the way that we size turbochargers. It changed the way that we select speed matches from compressor to turbine sides, and the way that we deal with turbine housing sizing. It really was a game changer in all those areas. And it actually ended up leading to the development of the HTE compressors that you see in the new XRE models for 2024. Those are specifically designed to maximize the benefit of the UHF turbine wheel by speed matching to those turbine wheels. Those turbine wheels want to run really fast. Okay. So you always want the turbine wheel of the turbocharger to be operating at its best point at the same time that the compressor wheel is operating at the point you want to operate the compressor wheel at. So you figure out where you're going to deal with the compressor, what compressor flow rate, PR, and whatnot we're at. We understand how much shaft speed and work we're going to do. Then we pick the turbine that can hit that shaft speed with the best efficiency, and also put the power band onto the shaft for this specific engine. So that's why sometimes you'll see the same compressor wheel offered with two turbine wheels. Okay. Well, a larger turbine wheel for larger engines, larger displacement engines, but then the same model turbocharger, but instead of having a 69S turbine wheel in it, it's got a 64S turbine wheel in it because it only got 2-liter motor. Changing the turbine wheel is kind of like changing the rear gear ratio in a car. Okay. Or tire diameter in a car. Okay. That's just, how am I going to put the power down? How am I going to apply the power? How am I going to get the power on the shaft? And smaller turbine wheels can accelerate faster because the gas comes in on the same amount of gas flow. The smaller shaft will accelerate faster, but at the same time, a smaller shaft can't put the same torque on the smaller turbine blades can't put the same torque on the shaft as larger turbine blades. So you have to really realize: am I trying to accelerate a lightly loaded compressor wheel of a small diameter, or am I trying to accelerate a larger diameter compressor wheel at a very high pressure ratio? And you decide the turbine wheel to do that particular job. So that's why you always see compressor maps, and the compressor map is not a turbo map, it's a compressor map. Right. Okay. It doesn't talk about the hot side of the turbocharger, and it's not the flow rating of the turbo. It's just telling you about the compressor characteristics. You need to also look at the turbine flow rate and turbine nozzle ARs when it comes down to deciding how to get the boost to come in the way you want on this particular motor. Yeah. So you got a 427 V8, it's a different application than a 3-liter inline 6-cylinder when it comes to turbine sizing. Even if the power level is the same, you wouldn't necessarily use the same turbine wheel. So, really? Yeah. Well, on really big motors, you make a lot of NA torque anyway. Okay. And true. And also on LSs, you got one exhaust valve, not two. So the VE of the motors at high RPM is different, and the torque onset that you're looking for is different. So just not the same stuff. And like a S front wheel drive car. Very different than a Civic you'd try to drive around on the street as far as power band. Yeah. They're launching at 8 or 10,000 RPM, on a turbocharger that's pretty big compared to what you'd normally use for a street. So the power band is like between 8 and 10,000 RPM or 7,500 and 9,500 RPM, something like that. Real narrowly focused, highly specialized to do this one job. Whereas, something that you wanted to drive around with air conditioning and, do tollway rips and, stuff like that, you want a wider power band, so you're not going to use an 85 millimeter turbine wheel on a 68 millimeter compressor for that application. You might use a 75 or a 70 millimeter turbine wheel instead. Right. To broaden the power band. Now, get the turbo to come in quicker.
Is it safe to say that, like, if you increase or decrease the turbine wheel, that if you run a bigger hot side larger AR or a smaller AR, that it affects how your turbo spools?
Turbine wheel is kind of like coarse adjustment for that, and
Okay.
then AR is kind of like fine adjustment for that.
Like, okay, so like let's say if you had a 0.96 hot side, right? Now that wheel, if you increase, or let's say if you decrease the size of the wheel, now you have more room in there, obviously for exhaust gases, right? So how does it affect performance?
So if you kept a 96, but then you changed from say like a 75 millimeter turbine wheel to a 70 millimeter turbine wheel, it's going to spool a little faster, okay,
Yeah.
as long as the turbine's not overloaded, as long as we have a compressor wheel on it that is not bigger than the turbine wheel. So if you go on a 68 compressor wheel and you got a 70 millimeter turbine wheel, then it's going to spool up faster. If you put an 81 on it, obviously it'll spool up a little faster even yet.
Right.
But if you got to be careful about putting smaller turbine wheels on, hoping for faster spool, because like I say, you run into the torque limitation because the radius,
size, basically,
the lever arm on the turbine wheel is shorter. You know,
Okay.
so the air that comes in, when the air comes in at a certain velocity, it hits the turbine blade. Well, if the turbine blade's that long and it hits it out here, well, it put more torque on the shaft, you know, because
Right.
there's a bigger lever arm. So these two things fight each other. And so you got to decide whether you're trying to put a lot of torque on the shaft or whether you're trying to put a lot of RPM on the shaft.
And it depends on the application, right?
And it depends on the compressor wheel too. Yeah. What's the compressor wheel want to do? You know, like XRE compressor wheels, they want to run about 20,000 RPM faster than a HTC compressor wheel. HTC compressor wheels have smaller trim and kind of loaf along a little bit RPM wise, while the HDE compressor wheels have a little larger trim and they want to really have more shaft speed on them to hit their best parts of their map. So having different size Legos lets you build exactly the little spaceship you want, you know?
Yeah.
So you need to have all these things where they can be somewhat interchangeable and tailor them for the applications. You know, sometimes you got a 3-cylinder snowmobile, sometimes you got a 10-cylinder Audi, you know.
Yeah.
They're all different.
That's just how it goes. Now, with these, you see these little like nuts on the front. Does that have any effect on turbo spool for the compressor side?
No.
Like if you remove this, or if it's there, does it have any, like when it's spinning at higher RPMs or when it's maxed out, does it have any effect on how the air comes into the compressor?
No.
Not at all.
Not at all.
Okay, because I did see something like that on social media.
Yeah.
About removing this nut and how it makes a difference in how the air comes in. And
They changed some other stuff at the same time. That's not what made the difference.
okay.
You make way more bigger changes to the compressor by moving the port around and the port angle and stuff like that than you would ever the nut. If you were to look at like a velocity flow field area of the inlet when it's like near choke flow, you would see that there's almost zero flow right in the middle above the nut. The air is turning as it's approaching the compressor wheel already. Okay. So you're moving all the air out at the edge. Okay.
Yeah.
That's where you have the most movement of air at the edge, and near the hub, you have the least amount of air movement happening. So you have to have really gnarly ass nut on there for it to get away. You know,
That's crazy.
Yeah.
Yeah,
You
no,
have 14 millimeter nut on a 64 millimeter turbocharger. Yeah, you might be blocking something. But
So it has, it's just probably marketing, you think?
it's great marketing.
Great marketing.
It's great marketing.
So how much more advanced can we get with turbos?
I don't know if we can get much better. Where we're at right now, we've just been optimizing for years now, and you know, short of some huge just shift in the approach to doing it, I'm not sure how much is really left on the table.
Yeah.
To be honest with you.
So we're pretty much there for the most part.
We optimized it, and then we took what was optimized and optimized it 4 more times, and then after we thought about it some more, it got optimized some more. So this is really kind of where we're at. You know, I mean, we're running out of ideas for what else to do to them to make them better. You know, really at this point.
Have any other companies taken your design or was patented? Like this whole wheel design that you guys have? Because why aren't other companies?
You can't. There's some things you can patent and some things you can't, and shapes you really can't patent. Okay,
Right.
like the Nike swoosh, that's not patentable. It's trademarkable.
Right.
Okay, but it's not patentable. It's just artwork. It's it's not. There's no patentable material there. You have to have some. You have to have some high idea if you want to patent it. Like on the Xona Rotor turbochargers, the variable preload for the bearing system was a unique enough idea to patent.
Yeah.
So there's a patent for that aspect of the Xona Rotor turbocharger because that's a mechanical system that has a goal and achieves it in a specific manner. Okay, so you see Chinese companies taking Garrett's complete catalog of turbochargers and making copies of the whole damn thing.
Yeah.
And Garrett and their entire legal department is powerless to stop them, aside from just rounding up a posse and heading over to China or something. There's not a peace. There's no peaceful solution for it.
Yeah.
Really, academically, if people want to be shitty, they're just going to be shitty.
Yeah. No, of course.
The day that Garrett releases turbocharger that have a UHF type turbo wheel in it, that's when I know I won. That's when I know I won. I'm waiting.
You're waiting?
Yeah. I've seen little Chinese guys copy me, but like I'm waiting for a biggie to go, God, we just can't get there unless we do that. I don't want to do it.
That's when you know you made it.
Yeah, that's when I'll know I made it. Yeah. When I got Borg Warner comes out with a turbo wheel that's like ours, then we'll have won. Yeah.
Is it like a consumer thing where everyone's like, well, I haven't tried that. I haven't heard my friend hasn't used this turbo, so I'm not going to try that. Like, why do you feel like, I don't want to say
it's not
you're
everywhere.
there,
It's not everywhere.
Yeah.
Well, we're a small company, first of all. Okay. We're not 3,000 employees and $2.5 billion a year, So we're just some guys that just decided we were going to make the best damn turbos and nothing was going to stop us. We weren't even going to let profit get in our way. So here we are just trying to make the best technology for turbochargers that we can, and we are. Why are we not the leading force in the market? We need to make more turbochargers. We need to make more sizes. As many sizes as we have, we don't have large sizes. Yeah, we launched with small frame turbochargers, basically from 45 millimeter inducer up to about 70 millimeter inducer, and that's how far we've got so far.
So you're at 70.
Yeah, 72 is as large as really we've made models of.
What does that flow compared to Garrett or Precision?
That's around 120 pounds a minute. A pair of those, you're over 2,200 horsepower on a 10 cylinder.
A pair of them. Mm-hmm. And what about one single?
Around 1,200 horsepower.
1,200.
Yeah.
So you don't have anything that's like, let's say if somebody wants to make 1,500, 1,600 horsepower.
Not in the Xona lineup right now. Well, okay, let me take that back because we have finally released the XRC 8082. So that's an 80 millimeter inducer with an 82 millimeter exducer turbo wheel on it. And we do have that on some V8s and some 6 cylinders right now. From what I've seen of it so far, I'm really excited about our foray into larger frames. Well, these would technically be like mid frames. A large frame would be like 55 size, like 90 plus millimeter stuff would be large frame. But this is a foray for us into mid frame turbochargers, and this uses what we call the X5C compressor, which is bigger than any of these models that we have sitting here. More along the lines of S400 size turbo. Yeah, more along the lines of like S400 size turbocharger, and that's an 80 millimeter compressor that's around 150 pounds a minute at its rated flow. So push it to maybe 160 pounds a minute. So you're looking at something there in 150, 160 pound a minute, 1,600 horsepower single turbo. And it's tailored for running, 35 to 50 pounds of boost in that range, So it's not really the turbocharger you'd use if you wanted to make 1100 horsepower at 1 bar because the compressor map is higher. The map is targeted for higher than that. But if you say you had like a 4-liter bar motor or a 3.5 liter inline motor or something like that, that would have the balls to push it,
right?
And appreciate the high pressure ratio range of it. HTC Compressor Aero is this HTC Plus is what is for 2024, which is a raised red line limit, speed limit for the compressor that adds a whole nother speed line to the compressor map and improves the rest of the efficiency in the compressor map at the same time, reduces internal stress in the compressor wheel, revised port geometry, increased flow rate for all the existing Xona Rotor models. So if you in the past had a XR 105-69S, that was a 72 millimeter by 99 millimeter HTC compressor that is being that is re-released for 2024 as an XRC an XRC 7269S. So and that is a higher speed rating and a higher flow rating than the 105-69S had, just because it's an evolutionary step of the HTC wheel. So HTC is kind of your mid pressure range focus, where sometimes you want a moderate boost pressure and sometimes you want a slightly more elevated boost pressure, or you need a dynamic range of because you're changing altitudes or something. And then HTE, which you find in the new XRE models, that is really catered for I'm going to run 50 pounds of boost. I might run 70 pounds of boost. So XRE is really tailored for all of it. And then the new LTA Aero is I have a really large engine that I want to run at a moderate boost pressure. Like I'm going to run it at 25 pounds or less, and I want it optimized for that range. So whether you need something that's optimized for a 2-to-1 pressure ratio, or a 3.5-to-1, or 4 pressure ratio, or a 5.5 to 6-to-1 pressure ratio, we have a compressor wheel Aero for you.
So anybody who's looking for any type of turbo, you got it down packed to it.
You just need to reach out and contact us, and we're happy to talk about doing engineering support for application and selections. No problem. Email us, call us. Yeah.
Now, if you line up all these turbos, let's say all the other companies compared to your turbo, what would make more power, you think?
For the sizes we offer, I think there's only probably a couple of examples where we get eclipsed by somebody, and that's somebody that's made a really unique, just special class turbocharger. Like you see right now in 68 millimeter class, there's a lot of crazy stuff happening. And like the let's take the nut off kind of thing, and it's basically kind of like look over here, but don't look over here, because what I'm really doing is over here. But look over here, I don't have a nut. And you in a turbocharger like that, you might be able to beat us on maximum flow rate, but as far as a range of operation, there's no comparison. You might beat us by 4% flow, but our operation range is like 5 times wider than your operating range. So maybe we're giving up a few percent right at choke flow, and that makes the fastest car not have my turbo on it. Okay, but we back off of that a few percent, and then we got the whole package just underneath that. So, and I don't mind it being that way, because there's just not enough class racers out there for it to matter.
Right.
You know what I mean? Like, so if you spend $100,000 developing something that was optimized for 68 millimeter class racing, that's great. And you're going to sell 14 of them. And then, well, good for you. Didn't you win? So yes, we could pay more attention to class racing. We look at it every once in a while. But until it's time for everybody to get ready for World Cup finals, nobody gives a crap about that stuff.
Yeah.
I
was thinking more of just a guy who, maybe he's got a 62 or 64, 66 or whatever he's got in his car, and he wants to switch over to Xona.
Okay, if you're talking about it's like standard comparing to like Turbine X PTE and the sub 72 millimeter range, we just whoop them, just front side, back side.
So you'll make more power.
I do a 540 Mick whooping on them.
So you're basically saying that any turbo like in that class, you're pretty much
skunk them. Yes, sir.
Okay. We got to figure out a way to get this, get you out there, man.
Well, it happens. It's happening. We have a lot of success with the people that we work with. If you look at stuff that Sissio is doing, IROS is doing, BBI is doing, other people that probably don't want me to talk about them are doing, we just hands down win, man.
Yeah,
it's just
I
like
know.
we can find people that are running a generic 72 millimeter turbocharger, a generic 66 millimeter turbocharger. We give them, if we can talk them into running what we want them to run, it's just sometimes hard because we end up trying to recommend a smaller turbo. Okay. And that's hard to sell because I could do that job with a smaller turbo and I'll make the power band wider and everything. But in the cases where they'll go ahead and listen to you and take your advice, they'll call you up and go, oh my God, I just took 76, 75 off and put your 72 millimeter on there and we gained 6 miles an hour. Well, how did that happen? How'd that happen? You changed the turbochargers and tuned it accordingly and the same pressure ratio, same boost pressure, and you made 6 more miles an hour. Well, I'm good, but that's what we see over and over again.
Yeah, that's what I've heard. I think Sissio mentioned it. Mo had mentioned it too on his build as well.
Yes, Mo's very nice setup that takes advantage of that too.
Yeah.
It's a very nice
So
car.
he actually was the first person that told me about the Xona, your company, because he has them on his Performante. And he also mentioned that you guys have a stainless steel turbine housing, so you don't have to worry about rusting and things like that.
We have a stainless steel turbine housing and a stainless steel bearing housing also.
Yeah.
There's not any real corrodable parts in the turbocharger as in the chrome steel shaft. So it does, it looks the part too. If you have a really nice car, that's really a situation where you're kind of hesitant to have a rusting iron bearing housing that's dripping rust stains down on your beautiful header, Yeah.
They usually run turbo blankets, but I feel like those things are pretty, I remember when I had one on my car years ago and the fiberglass is always in the air and it's just,
I don't like it. It just makes me I mess with a turbo blanket. It makes me want to hold my breath.
Yeah, no, seriously.
I don't want to breathe that stuff.
I
don't know. I turbo blankets ick me out. I just like heat shields. I like stamped heat shields. They see the little wavy Inconel form fitted heat shields. Yeah, that's the bomb, dude. I wish I made those.
Yeah,
I want to make those. Those are
pretty cool.
Those are badass, and it's perfect. You know what I mean? Because the wiggly, the corrugated nature of it keeps it from being stuck right up against the housing, trapping the air there.
Yeah.
Okay. Air can circulate underneath that. Okay.
Right.
So when you insulate something with a layer of dead air and then a radiant heat barrier that also has some conductivity barrier built into it, like maybe a multi-layer Inconel sheet that has maybe a glass layer in the middle or something like that, you are having an incredibly effective heat shield that doesn't result in your hot part getting hotter.
Right.
The object of the heat shield is not to make the hot part hotter by trapping the heat in. You might want to do that for some weird application, like you got the Formula SAE guys that try to get 200 miles per gallon on a Briggs & Stratton motor. They wrap in the whole thing with insulation because they want to keep all that heat in there because they don't want to wait. They want to put any more fuel in it than they have to. So you want to keep all the heat in there. Okay. So there's weird reasons why you do want to trap the heat.
Right.
But it doesn't have anything to do with going fast. Okay. If we're going fast, we need the housing to stay inside of its operating range.
Right.
Things get weaker when they get hotter, right?
Yep.
Okay. So a housing that can stay a little bit cooler is a stronger housing than a housing that's glowing red. Okay. And we talk about containment. We talk about blowing things up. If it's glowing red, it's weaker than if it wasn't glowing red. Okay.
Right.
So if we can keep the heat from getting these other parts hot, but not make the hot thing hotter, then you've done the right thing. Then you've done the job well. Okay. But if you just take in heat wrap and just wrapping that part, and now the part is 200 degrees hotter and the stuff out, you protected this other side, but you made the hot part 200 degrees hotter, then you achieved one thing, but you made yourself a new problem that you might not know about yet until your material starts to fatigue and break and crack and corrode at an accelerated rate.
And the stainless steel kind of prevents that from happening?
Stainless steel does. The nitronic stainless exhaust housings totally keep that from happening. Okay. And not only that, grab that cartridge right there and turn it around. The bearing housing is also stainless steel.
Oh, this is cool.
The middle of this, the bearing housing is stainless steel. This doesn't rust either.
Wow.
Okay, so not only is the exhaust housing non-corrosive, but the bearing housing is not corrosive either. So, like a lot of times you'll see a guy with a really nice car setup, but the bearing housing is just like bright red rusty.
Yeah, rusted.
And sometimes you'll see people try to powder coat those or ceramic coat the bearing housings and stuff like that.
Though.
But it's kind of weird, and it's in a lot of trouble to go through. But I mean, if you're only going to make turbos with iron bearing housings, then I guess it's what you have to go through if you want it to not corrode.
Yeah.
So it's what I like about these. Very lightweight bearing housing too. This is a brand new redesign for 2020.
It feels like it's well built.
And even in the containment failure thing, you see the plate bent and distorted, but the plate didn't break either.
Right.
So all the pieces are designed with strength and burst containment in mind.
Oh, that's pretty cool. Mm-hmm. That's dope. Mm-hmm. So do you feel like a lot of the Lambo guys are pretty much, because a lot of Lambo guys, the V10 guys are pretty much using your, not using your stuff, but they've had great success with your
When you get to that level of doing a project, you're less headstrong about how to do it, and you're more interested in hiring people that are the best and getting the best result.
Okay.
So you end up with really good project managers when you get guys that want to build those projects.
Yeah.
Okay. They don't necessarily want to change the spark plugs themselves, but they know how they want their project to go, and they hire people that are experts, the best in the field, and then they follow their advice. And what happens? They end up with great projects as a result of that. They end up with stuff that works better than anything else. When you trust your experts, you end up with the best results.
That's true.
I don't know.
That's true.
I get on the phone sometimes, and I'll try to explain something to somebody, and and a guy will just go, "Well, that's just your opinion." I'm like, "It is my opinion. It is my very educated opinion."
Yeah.
yeah. And it's the opinion that you spent time out of your day to call me and get, and you should be a little bit more grateful for it, man. I'm not just filling you with hot air. I'm answering your questions as accurately and concisely as I can and give you the best advice I can. It's not just my opinion. It's based on all of my whole life experience. I don't do something else. This is what I do.
Full time. This is it. You 100% turbo.
Since the 90s.
Since the 90s. Since the FP red green days.
Mm-hmm. Since before then. Yeah. I was building turbos for another guy for a while before that. So yeah.
Yeah, FP was
the Frankenstein era of the late 90s. Yeah.
So that was actually one of my boy that I was telling you about earlier, Mike. That's how I kind of knew about those turbos. The FP red, green, it was black as well, right?
Yeah. We ended up making a black model also. The idea there was to have model names that meant something and that crossed applications. So whether you had a Subaru or an Evo or a DSM, whatever you had, you knew that the green model was the well-behaved, good street version that maximized the factory motor. Okay. And then you knew the red one was the nice, well-rounded, still kind of streety, but better off if you had done cylinder head and camshaft upgrades and had a little bit more mojo going. Okay. And then the black model was like, I still want direct fit, but I want another 150 horsepower bump even more, because I'm only factory fit application because I want to race in factory appearing class. So and then the zero in some applications I put a zero model after the black model, which was just an even bigger version of it, but still direct fit.
And what were some of these guys making? Or just I can't really call it.
Black models, you might make on a DSM on a black model, you might make 650 horsepower or something like that. Zero, you'll make more than that.
Yeah, back then those are big numbers.
When we first started making red models, like I was getting small notebooks out the other day, and I found a faxed dyno sheet from Dan Kokic at Proven Performance, where he had made 520 wheel horsepower in his red model, and it was like 2002.
What?
It was something like that. And I was like, man, I'm so glad I have that. You know what I mean? I don't have a fax machine anymore, but I had that fax, because they had just got back from the dyno, or they had a dyno at his house, at the shop there. And they had just done that and faxed that over to me. And, it's neat to just see how, over time, we just keep inching up. We just keep inching it up and inching it up and inching it up. And everybody always wants to say it's not a race car. And I'm like, how much power are you making? They're like, well, it's about 700. And I'm like, and a 4-cylinder motor. So that's what, 180 horsepower per hole? That's a race car, bro.
Yeah, that's fast. That's quick.
Yeah. What if you had 8 of those cylinders? Okay. It would be a race car, right? Okay. Just because you have 4 cylinders doesn't mean, from an engineering perspective of the cylinder pressures and the challenges of keeping it bolted together and not bending stuff, it's a race car.
Yeah. So how do you feel? So do you feel like around, like for the FP, like that whole time period that has kind of helped you innovate these products nowadays?
Oh, definitely, man.
Yeah. Like that mindset pretty much.
I go to eBay and type turbo sometimes just to look at the parts are there. And I see a lot of myself when I go to eBay and look at turbocharger parts. I see a lot of myself. I see a lot of parts that are just basically just exactly the part I developed, just maybe a little Temu version of it, but almost, almost enough, and if eBay had turbo parts on it in 1999, like it did today, man, I would not have been able to resist it. I would have been Legoing eBay parts together and just seeing what happens. And I don't really hold any of these garage guys. I don't really hold it against any of these garage, guys that experiment and try with stuff. I mean, I think it's cool. You should do that. If you're so inclined and you think you can be safe enough, why not?
Yeah. So basically,
have fun, dude.
Fun,
yeah. I mean, I would eat it too. If I was in your shoes, I'd be eating that too.
I remember those days, like the CX Racing Turbo days.
Oh gosh, man, they used to epoxy the compressor halves together.
Yeah.
Okay, that was how crappy it was in the beginning, man. That they had 2-piece compressor covers that they glued together.
Yeah.
It was nuts, dude.
But they were so cheap though, man.
And flapper arm linkages in the turbocharger, where it's a piece of 8mm rod that's just bent and mashed flat at the ends so they could drill a hole through it. I mean, it's in some cases it is the most turbo looking part you could buy.
It's the most turbo looking. That's true. Literally,
it's very turbo looking.
No, 100%. But those days were cool though, because I feel like, you were able to get parts like that, blow up if anything, and then just get another one. Or budget friendly kind of builds and stuff like that.
And I'm sensitive to the budget friendly builds. That's why I started the Happy Dragon line, the HD line of turbochargers. It's really basic turbochargers for. I started to realize when I started working with LS guys and I started my own LS projects. What was that? Right around 16, 17, I started doing my own LS projects. And I really learned a lot. I mean, the first 2 years of that was a big eye opener for me. I had a lot of misconceptions about what you could do with a junkyard Chevrolet motor. I was wrong. You could do a lot with a junkyard Chevrolet motor, okay? And I finally came to get it. Okay, what I was missing when I started. What I was missing when I started was the perspective on the budget for the project and what the goal was. Okay, it's like about grins per dollar, basically, is what this is about. Okay, so if you go and pull a junkyard motor and take it home and pressure wash it and pull the pan off, pop a couple of rod caps, convince yourself it's all right, slap a different cam in it, hand port the heads, put some springs in it, and put it back together and drop it in your truck with a turbo on it, you have not spent $2,000 yet.
Yeah.
Okay. You might have spent $2,000 or $3,000. Okay. Why are you going to buy a $3,000 turbo? You're not going to. It doesn't fit. Okay. Yeah. You need to buy an $800 turbo. You need to buy a $1,500 turbo. But you're just not going to put a $3,000 turbocharger on a $3,000 motor. It doesn't make any sense, And I got $3,000 turbochargers. See behind me, I got GTX 50, 55. That's behind you. Yeah, behind you. That's
that one.
So that's a GTX 50 85. I think they call them 133, 50 GTX 5033 or something like that. It's like an 85 millimeter. This looks the same, and it's the same size and form factor, okay? But this is a journal bearing S400 that costs less than $1,500.
What?
Yeah. And if you're going to run 15 or 25 pounds of boost, you won't know the difference between that $3,000 ball bearing turbocharger and this one. You can't tell. And you're not going to have a problem running this journal bearing S400 at 25 pounds of boost or even 30 pounds of boost. You're just going to make your 1,000 horsepower or your 1,200 horsepower or whatever it comes out to based on your application.
That looks expensive.
You don't have to spend thousands and thousands of dollars on turbocharger. Man, I had this discussion just on Facebook the other day. Somebody said, hey, what about these Force Performance HD 5598 turbochargers? Anybody run these? They sure seem awful cheap. I'm a little worried, and I was like, I could sell them for more if you want. Okay. But I'm trying to be Johnny Appleseed out here and let a lot of people have good stuff.
Yeah.
And if you're going to run 25 or 30 pounds of boost and you've got good oil pressure, and you're not going to cut those 160 foots and have those oil pressure problems, then you can run a journal bearing turbocharger. And I'll tell you a secret, on S400s, they got so much thrust bearing in them, they can suffer a few bubbles. It doesn't just take them out like a T4 or a Mitsubishi TD06. Yeah, an S400 is designed for a great big diesel, 8-liter motor. Okay, so it's got big surfaces in it. It's ready to deal with lots of load. It's not the lowest inertia system. It's not the lightest weight system, but it is made out of cost-effective materials, and it's not that much heavier. And so when you start weighing these things, you start to realize, what does an LS guy need, or what does a budget project need? A lot of times, if you could get a ball bearing 35R for $700, you're just trying to get this RB26 running this weekend anyway. Okay. I'm not trying to break a record or anything.
Yeah.
Okay. I want to put this car together and I want to go to that empty parking lot and I want to do donuts, and if that's what you're trying to do, then you don't have to spend $3,000 on a turbocharger. You can spend $500 or $700 or $1,500 on a turbocharger. Go out there, have some fun, figure out what all your problems are, because you're going to have a bunch of problems you don't know about yet. You'll find them, okay, but you're going to have a lot of problems you don't know about yet. Like the fuel line's not big enough, and that fuel pump you thought was big enough is not big enough, and those injectors you bought suck, and all these other things you're going to find out. But you're not going to find out until you buy the turbocharger, bolt the shit together, and try to run it. So if you're waiting to do that until you have the perfect $3,500 turbocharger, you're just delaying your whole project. When you could just go ahead and buy an $800 turbocharger that lets you put the whole thing together, debug the whole deal. You need to learn how to drive it anyway, right? So, you need to learn how to tune it. You need to learn how to do all those things. So start with the budget stuff, get it together, work the bugs out of it, go from there, man. Maybe you end up selling the whole damn car to somebody that just saw how much fun you were having and walked up and go, you take 10 grand for that? You just don't know.
Yeah.
So, the whole idea of like, well, I'm going to buy the right turbo because it's going to be perfect for my next engine. Bro, when are you going to build the next engine? You haven't built this damn engine yet. You know what I mean? So don't plan for, oh yeah, this will be perfect when I get the bigger heads, or this will be the perfect turbo once I change to that 6.2, but I just have the 5.3 right now, but I'm going to buy the turbo for the 6.2. Don't fall into that pitfall of later.
Yeah.
Go ahead and buy what fits now. And budget is a perfectly good reason to select one turbo over another. Perfectly good reason to select one turbo over another.
I hear that a lot with people like yourself who are at this level, like the same thing. I'm sure it's probably obviously conversated with customers.
In my own cars, I have a whole array of turbochargers. Okay. Like I have like my Talon Xona Rotor ball bearing turbocharger, but it launches. It's got slicks on it. Okay.
Right.
Okay. My Turbo Tahoe, the boost hoe, journal bearing 7875. If it runs a 1960 foot, that's too quick. Okay, it doesn't have the rear suspension for it. It'll wheel hop. It just needs to come out nice and easy. So I don't have any problems in the boost hoe. I run it at 15 or 18 pounds of boost. I don't need a $3,000 turbocharger to run 15 or 18 pounds of boost. I just did Rocky Mountain Race Week with that boost hoe a month or two ago, and I had the most fun I've had in years. Just driving from track to track in the Tahoe, pulling up, making a couple of passes, going home. I was racing in the 11.0 index class for that, and my problem was how to not run 1090s. So I had a great time.
Yeah,
I had a great time.
That's awesome.
So, even in my own cars, I have a whole array of turbochargers.
Different turbochargers, different budgets, not even the most expensive stuff.
Yeah.
Even as the owner of a turbo company.
Even though I could totally treat myself and put expensive, my own expensive turbochargers and write it all off and everything. Okay. Nobody's going to have lower cost of entry into putting expensive turbochargers on their projects than I do.
Right.
And I still don't have the super expensive stuff on all my projects.
Oh, well, there you guys have it. If you guys are on a budget, it's okay to be on a budget, guys. You don't have to spend $4,000 on a turbo for the next set of heads or whatever the next project is going to be.
Mm-hmm.
Just build it right for whatever the current setup is.
Have your fun today, man. There's no promise of tomorrow. So
yeah. All right. So what's next for you coming up this year? You have a couple events you're heading to.
We are about to head to Ohio to Summit Motorsports Park there to participate in the IDRC DSM versus the World Shootout. Okay. It's about to happen in the first weekend of September, and I'm going to be racing my talents. I'm really excited about that. Okay. Normally I go to that event and as a vendor, and I spend all day in my booth, shaking hands and kissing babies and stuff like that. But I've done that the last 4 years or so, and I'm going to race this year. So taking my race car up, and I'm just going to enter a street eliminator. I'm going to be a slow car in that class, but I've seen enough shootouts to know that it's often a slow car that wins that class. So when you race DSMs, it's a lot about just making pass after pass after pass, and they're all good, solid passes, and not breaking your stuff.
Yep. That's what it's about with those.
So you got to cut a light, and you got to make a bunch of passes. So I'm getting really excited about that. I think beyond that, I don't know. I will be doing some stuff. Xona will be doing some stuff in Florida this fall. Fernando Ostar's got some stuff lined up at the end of this summer, beginning of the fall. We'll be out boothing at that event, FL2K, I think, and then we're going to be doing the GTR event in Ennis, Texas.
Yes, I'll be there.
Yeah,
GTR
right,
Festival.
Yeah, we'll be there. Yeah. That's going to talk to our Australian brothers at that event, and I'll be boothing. I don't have one of those cars, so I'll be there. It's a local event for us, so I'll be boothed out, a full force booth at that event. Sponsoring that event, so you can come by and visit and come by and see me. Bring me cold beer if you come by and see me.
Yeah, come by, hang out. I'm definitely going to stop by and say what's up. Who knows? You might even be close to each other with the tents.
Yeah, good.
That's going to be fun. That's going to be fun. Well, I appreciate you. Thank you so much, Robert, for having me.
You bet. My pleasure. Thank you.
Super accommodating the whole time, Even with the street tacos, fire. Make sure you guys check those out too if you guys are ever in town. You ever stop by, make sure you can get those street tacos.
Stop by Arroyo's.
So can you tell the viewers where to find you on social media platforms, website, and everything
absolutely.
else?
So XonaRotor.com is a great place to see the newest releases from Xona Rotor. ForcePerformance.net is where you see all of my Force Performance-based turbos, all of my Happy Dragons and FP-based turbochargers for Subarus, DSMs, and Evos are there, as well as all of our Xona Rotor offerings. Xona compressor maps are of course listed there. Yep. You can check us out on Instagram at the same at Xona Rotor Instagram and Force Performance Instagram. We have a lot of content that we keep up there, and our Force Performance YouTube channel. We're really trying to do a better job with that and have more consistent releases. But we do have a lot of videos there about tech talks that I've done at different places, and also just project videos about stuff that we've been working with and messing with. So a lot of fun videos there to watch. So
solid. That's fantastic, man. Thank you so much, bro. Appreciate it.
My pleasure.
I'll be looking forward to seeing you at the future events as well. We'll be at GTR Festival. Make sure you guys come hang out, check out his booth as well. If you guys are listening and watching, make sure you guys like, share, comment, and subscribe, and make sure you guys listening on all streaming platforms. Until next time, guys, we will catch you on the next one. Peace.
Boost on, y'all.